Um, in a way, a lab test can be very easy, but it's hard work. It is actually hard work to get ready for it. And the good news is we're going to be ready, get ready today, we're going to get ready tomorrow, and then you still don't take it till Thursday. So you have plenty of time to get ready for it. So, yeah. All right, so let's go over a quick review. Remember this chart here? Does everybody remember what that is? Okay, now why did I even bring up that lesson? Because we had one lab over here where you had to heat the copper. Does copper react with oxygen? Does copper react with oxygen and to form this stuff here? What do you think? Does it do it or not? Okay, but why doesn't it do it? Why did I have to put it into a burner? What was the idea of the little mini lesson yesterday? I don't remember on experiment number 2, when I put that nail in the solution, do you remember me having to heat that up? No, that one occurred spontaneously by itself, didn't it? But some experiments in science, and that's what I wanted to teach you today, some chemistry reactions, they don't take place by themselves. They have to be pushed a little bit. What do you call the amount of energy it takes to actually get the reaction started? Activation energy. Okay, so one of the questions on the lab test will say, when you heated copper in a flame, why did you have to heat copper? Because you had to give it some activation energy, didn't it? Now, by the way, let me go ahead and balance this a little bit. 2 here and 2 here. All right, does everybody know how to do a balance equation for number 1? What do you think? One of the things in your lab report says write a balance equation for each reaction. Did everybody? Is that what you guys had already? Or you never thought about it? They'll be quiet here in a minute. Okay. So anyway, so part of the mini lesson had to do with that one. How about number 3? Did we have to add some activation energy on number 3? See that table over there where you had that blue crystals and you heat them in a bunch of on the test tube? That needed some activation energy too, didn't it? Okay, so that applies to at least 2 of the reactions. Now, let's go over here. What is this graph showing? And by the way, let me mention it again. The reactants here are the reactants. The reactants had a certain amount of energy in them, and when they got done, what can you say about the amount of energy here versus here? Is if you ever have less energy in the products than you did in the reactants, then it's exothermic. So see this right here? This is exothermic. Okay. Now, let's go to, do you remember that table over there where you had to add water to a kind of a white crystal and then you felt it? Do you remember something really unusual about the test tube? It got really hot, wasn't it? I had cold water, I had cold crystals, but then it got really hot. Well, then here's what must have been happening. You must have had that on table 4, you must have added water, and what happened is with the products that got done must have had, the products, I made a mistake. The products must have had less energy than the reactants. See that? And I'll go ahead and write that one for you. That one was this one. We had this stuff called CuSO4, and you added water. And what happened is it turned into this. Okay, now I don't want to get too fancy here, but this stuff here had a certain amount of energy to it, and this stuff here had way less energy in it. And so what happened is a lot of energy was given off in the form of heat, wasn't it? So that has to do with that lab. Okay, now let's go one more panel over here. What does this have to do with anything? What is it that could cause the amount of activation energy to be less? And what's the new word on this panel And that was on the last table. On the last table, here's what happened. You had hydrogen peroxide. Does everybody know what hydrogen peroxide is? H2O2? Yes? Okay, now, watch what I'm doing here. The manganese dioxide, where do I write it? Why didn't I write it on the left of the arrow? Is it a reactant? I mixed it. And why don't I write it on the left? Why don't I write it on the right? And so what do you call this chemical that's going to help the reaction take place, but it itself is not altered? What's that word? It's a neat little word. If you took chemistry and somebody said, and you used the word catalyst, I'd say, woo, that's a pretty fancy word. And so we had here, we don't put this on the left, we don't put it on the right, because it's not a reactant, it's not a product, it's a catalyst. Now, does anybody happen to know over there what happened there on table 7? What happened to the what happened to the hydrogen peroxide? You should know at least one of these. You had to test for what gas? What gas were you testing for? Oxygen. Now, you had to look up, and that's why part of this thing is research. You can use your phones. What was the other product of this decomposition? This is a decomposition, isn't it? Okay, what's the other product? Who knows? H2O, right. Now, if we had to balance this, and again, on the lab quiz, on the lab test, you will have to write a balanced equation for every one of these reactions. You get it? That's a no-brainer. It's going to happen. Okay, so now, how do we balance this? What do you think? Any ideas? I know whatever I put in front of here, it's going to give me an even number of oxygens and an even number of hydrogens, right? So I probably don't want to put an odd number there, do I? So I'm not going to leave it as 1. I'm going to try this. Okay, now how many hydrogens does that give me? 4? 4. How many oxygens is that? 4. 2 plus 2. What do you think? So if you hadn't already figured out the balanced equation for number 7, there it is right there. Now, why do I want to teach this little mini lesson? Because what was the catalyst in that reaction? What was it called? And because it's a lab test, I'm going to ask you that. I'm going to say, what is the name of the catalyst? And what are you going to say? Okay, there are 2 names. The name on the bottle said manganese dioxide. What would the name in the lab packet say? I keep looking at your faces because I can't tell. The way I would have taught to name this one is manganese 4 oxide. See, manganese 4 oxide, that's a 2 there, or the bottle said manganese dioxide. So the next question would be, what color was the manganese dioxide? And if you don't know, it's like, that's some of the easier questions on the lab test. You were there, right? Did you go back to that table? What was that? What color was that stuff that you put in the hydrogen peroxide? What color is hydrogen peroxide? If you have to know because you were there. Ready? And those are the easy questions. Everybody know? Raise your hand if you know what color the hydrogen peroxide was. Just raise your hand. Okay, now raise your hand if you don't know. It was clear. It looked like water. Okay, now next. What color was the... Raise your hand if you know what color the manganese dioxide was. Now raise your hand if you don't know. You better find out. If you didn't raise your hand, you ask your partners today, what color was that? All right, okay on that? Let's go flip it over here. Let's do this one. Do you remember back there, number 5, I will ask you this. What is the balanced equation? This is the hard one. All right, what are the two things you put together, the 2 liquids? Real quick, come on, help me out. Sodium carbonate. How do you write sodium carbonate? Sodium is +1. Carbonate is -2. That's why you need 2 sodiums, right? Now, why am I putting AQ after that? Because it was dissolved in water, wasn't it? What was the other reactant? What was it? Calcium chloride. Calcium's +2, and chlorine's -1. Is that right? And was it also aqueous? Yes or no? You got to help me out here, okay? I got to get some visual aids. I can't even see Sean. Sean's hiding behind. Okay. Sean, I can't tell if you're understanding this or not. What do you think? Now, what kind of reaction is this? Think about it. AB plus CD. What do you think? I think it's going to be double replacement. All right, so now, what are the 2 products going to be? Somebody, Hayden, help me out here. 2 products. Just give me the name. Give me the name of the 2 products.
Sodium chloride.
Sodium what?
Chloride.
Okay. And how do you write sodium chloride? You look on a periodic table. Sodium's what? +1. What's chlorine?
-1.
Okay. Now that works, doesn't it? Here's a mistake that first-year chemistry students make all the time. They saw Na2 over here, and they thought I was right Na2 over here. I've never taught that. I've never taught that. I said that sodium will form a compound with chlorine, and calcium will form a... I've taught that. But how does sodium form a compound with chlorine? See that? Now, what's the other compound? Hayden, go ahead. You did a great job on that one.
Calcium.
Well, no. What's CO3? Carbonate. Now, calcium on the periodic table is +2, and what's carbonate? Okay, so that works, doesn't it? Now, there's one more thing we need to do here. What do I put after this and this? Do I put aqueous or not? So that's what this chart's for. This chart is for a double replacement reaction, and you want to look up the 2 products. So the 2 products are sodium chloride. Let's go down here. Sodium chloride. Chloride. Sodium chloride. And what does AQ mean? Okay, so I'm going to put AQ after this, and that means you'll never see it. I never saw the sodium chloride because it was what? It was dissolved, and I never got to see it. What about calcium carbonate? Calcium. Uh-oh, I went too far. Calcium carbonate. What does it say about that? It's going to be a solid, isn't it? It's going to be a solid. That means it's insoluble. It will not dissolve in water. Therefore, you're going to see it. And the most famous chemistry word that has to do with this kind of reaction is, what do you call an insoluble product? Now, where do you find products in chemistry? On the left side or the right? Okay, so this one was soluble. I don't have a special name for that. What do you call an insoluble product? Starts with a P. It's your new word for yesterday. What is it? I made a big story about rain and snow.
Precipitate.
All right, precipitate, yeah. Precipitate. Okay. And so this is not only a double replacement reaction, it's sometimes called a precipitation reaction. All right. You okay on that? All right, so now we have one more little mini lesson. And what I'm going to do is I'm going to make you do maybe 1 or 2 of these required, and the rest would be extra credit if you get it. And I'm going to show you a little lesson here. What else do you know? Single page synthesis. Okay. All right. Now, okay, I want to show you something here. These have been taught to you already. These are the 5 that I usually teach for first-year chemistry. And we know that you actually are very good at classifying reactions. You're very good. I do want to show you, though, there's something interesting about this. Of those five, like the reason that one I just showed you, the reason that one happened, and what is it that made the reaction took place, is because the formation of a solid. And we now know that word is called a precipitate. Okay, now, what was the reason for that again? Because when you put them together, there was an insoluble product, a precipitate, and that's what made the reaction take place. Does anybody, let's see how smart you are today, okay? What if I had used sodium nitrate and calcium chloride? I would have gotten sodium nitrate, and that's soluble, and I would have gotten calcium chloride, which is also soluble. What would happen if both products were soluble? You put the two things together, and what would you see? I'm going to see how smart you are today. What if I'd use not sodium carbonate? What if I use sodium, let's use sodium chloride. What if I use sodium chloride and calcium chloride, and they come together, and you said, well, I know what's going to happen. You're going to get calcium chloride and sodium chloride, or you're going to get the same thing. So what do you think would happen? If you put these two liquids together and both of the products were soluble, what would you see? Okay, I lost you on that. I lost you. Everybody look at me. Did I lose you? What if you did a reaction and both of the products were soluble? Anybody know what that means? What is it? I know that's what aqueous means, but what does it mean if I had a chemical reaction where both products were soluble? Both reactants were soluble and both products were soluble. Maybe it's too high level. If this was sodium nitrate, that's soluble, then I would have gotten sodium chloride and calcium nitrate, and that's soluble too. Now, okay, all right, 30 more seconds, then we'll move on. If both of these products had been soluble, you would not see anything, and nothing would have happened. There would be no chemical reaction. But what is it that made the chemical reaction take place? One of the products was insoluble. One was the precipitate, wasn't it? That's why the reaction actually took place. Otherwise, it didn't even take place. You can put two things together and nothing happened. Or you can put two things together and something happened. Okay. Wait. I'm going to show you that of these five, one of them, the reason it worked is because of that. But now, I'm going to show you this one. Okay, now see this? The reason that all four of these work is because somebody is going to gain electrons and somebody is going to lose electrons. So if you ask me, why do most chemical reactions take place? It's because one of the chemicals is going to gain electrons and one's going to lose. Now, I want to show you a couple fancy words here, okay? You're okay. All right. If you lose electrons, it's said to be oxidation took place, or you're oxidized. Okay, now, so oxidation. Have you ever heard anywhere of anybody telling you where something got oxidized? Okay, when you see rust gets oxidized. Anyway, so I'm going to show you how to memorize this in just a minute. If you gain electrons, you're said to be reduced. Okay, so let me show you a little memory trick, all right? Let me show you a little memory trick. Leo, the lion, says grr. And I'm going to say grr like this, G-E-R, okay? Now, what do you think this stands for? If you lose electrons, you got what? Oxidized. If you gained electrons, you got reduced. That pretty neat little memory trick? So Leo the lion says grr. All right, ready? Zach. Hey, Zach. Shut up. Head up. Okay, now, what I'm going to do is I'm going to show you experiment number 1, and it might be the only one I ask you to do. All right? All right. Here we go. Tell me what happened to number 1, and anybody who's been here should know because I just did it. All right, Aiden, I'm ready. Tell me what happened to number 1. At table number 1, tell me the chemical equation.
I haven't searched it up yet.
You haven't what?
I haven't searched that one up.
Yeah, but I gave it to you today.
I did.
Why don't you just think about what happened? Tell me what happened today. What happened at that table? What do you remember doing? Oh, let me tell you the best way to study for the lab test. Get a group of people and sit there and say, tell me everything that happened when we went to table 1. You're going to say, well, we went there and picked up a piece of, what was it, Aiden? Copper. And we heated it in a burner, didn't we? And why we did that, we had to add some activation energy, didn't it? What did we want to happen to the copper? What did we want it to react with? What did we want the copper to react with?
Oxygen.
Where? From where? Not the burner. The air. And the air is about 20% oxygen. It's there, isn't it? And how do you write oxygen?
O2.
All right, is everybody okay so far? So we took a piece of copper and we heated it, hoping that it would combine with what? Oxygen in the air. And what did we, when you did a research, we found out what was made.
CuO.
And it happened to be, it could have been copper 1 oxide, but it wasn't. It was copper what? It was copper 2 oxide, wasn't it? And let's go ahead and balance the equation. 2 oxygens, 1. 2 coppers. That's several questions on the lab test. There it is right there. Okay. Now, what I want to ask you is, who got oxidized? Who got oxidized? Well, our memory trick is what? Leo, right? If you lose, now here's where you got to trick your brain a little bit. Now watch what I'm doing here. If you lose negative electrons, what happens to you? If something were to lose negative electrons, wouldn't it become more positive? If you had the same number of electrons and protons, and let's say you lost some of your negative electrons, wouldn't you become positive? So let me ask you, let me show you how to do this. And this is a minor part of the test, okay? This is minor. But when copper's only +2 or +1 when it's in a compound. What is copper when it's not with any other element? It's copper metal. It's not an ion. It's not an ion. It's 0. It's copper 0. And what is oxygen when it's not in a compound? It's 0. Now, look at right here. This is something new for you. Did something change their charge? In this reaction, was there somebody who changed their charge? I started at 0. Did I end up at 0? No. I changed my charge. I started at 0. Did I end up at 0? No. And you know why this reaction is taking place? Somebody's going to gain electrons, and somebody's going to do what? And we're going to figure it out. All right, here we go. Who got Leo'd? Who got oxidized? If you lose negative electrons, you become more positive. Think about the number line. -2, -1, 0, 1, 2. If you become more positive, you're going that way in the number, right? Which one of these elements got more positive? Which element? Okay, copper. Look at copper. Copper started out as what? 0. Now, how did it end up? Did it end up as 0? No. Now, ask yourself this question here. How does something go from 0 and jump all the way up to +2? He must have got rid of or lost. He lost, well, how many electrons would it take? How many electrons would you have to lose to jump from 0 all the way to +2? 2. Everybody got that? Does that make sense here? The reason this reaction even takes place is somebody's going to gain electrons, but you cannot have somebody gain electrons. I'm sorry, you can't have somebody lose electrons unless somebody does what? So who got reduced? Who got reduced? All right. If you gain negative electrons, what happens to you?